So I will say simple interest does compound once per year or annually. So if someone said we were going to compound our interest annually, you would just be using the simple interest formula. And then we also specify n equals 1, n where n is going to be the number of times we compound per year. And then there's other frequencies. So other frequencies could be frequencies of compounding. Someone's trying to get into the class. I should let them in. So there's lots of things you can write for how often we compound it. Going from like long and short, we could do semi-annually, which would be twice per year. So that would be n equal to 2. We could do it quarterly, where you'd be compounding 4 times per year. You could do it, I mean, you could make up all kinds of stuff. You could do it like triannually, which would be 3 times per year. You could do it hexannually, every 2 months, 6 times per year. Those are kind of strange ones. You can do it monthly, where n would be 12, right? 12 months per year. You could do it daily, n equal to 365. And those are kind of the most common. You can come up with some other wacky stuff like, oh, sorry, I guess I forgot weekly. Weekly would also be a good one. Weekly, where n would be 52. So these are the typical kind of amounts. So if someone says we're compounding weekly, you know that n is supposed to be 52 weeks per year. Great. So here is the compound interest formula. So the way we calculate compound interest, and again, so this is the amount of money after t years. I usually like this. In the notes, there is no a of t, it's just a. It's fine. Equal to the principal times 1 plus. Now, instead of being 1 plus r to the t power, like it was for simple interest, it's going to be 1 plus r over n to the nt power. Let me label all the things again. And they are labeled in the notes. So this is the amount of money after t years. P is the principal or initial investment. N is the number of times per year that we compound. R is still the interest rate as a decimal. And T is, once again, the number of years. So this is the formula for compound interest. Oh, yeah, I can go. Oh, okay, you said never mind. All right, cool. So this is the whole formula. You could memorize this. It comes up somewhat often. You might memorize it. It'll certainly be available to you on an exam, so you probably don't have to memorize it. So let's talk about how this works. So here's the first example. Let me go over to the other side. I was listening to the radio the other day and they were talking about how apparently podiatrists have seen a real uptick in people coming to them because a lot more people are not wearing shoes in their home, like they go to work and stubbing their toes. And I feel like, oh, I'm definitely one of those people who's not wearing shoes and stubbing my toes. I haven't had to go to the doctor for it, but who knows? Maybe I will. Sorry, all right. So there's our formula. And we're just going to throw our stuff into the formula. We're going to talk about kind of how it's different than the simple interest formula. So here's the example. We have $1,000 to invest. And our options are to invest for 10 years. And our options are either option A, an account with 6% interest, 6% simple interest, I should say, meaning it's only compounded annually. So we know with simple interest it's n equals to 1. Or option B, 6% interest compounded monthly. And as you might be aware, if the interest rates are the same, then you're always better off, or you'll get more money the more frequently you compound it. So we're going to find, not surprisingly, that the second option is going to be the one that gets us more money. Well, let's calculate both anyway, because there's something I want you guys to see. So let's write down all the important things. Let's see. Our principal is $1,000. Our interest rate is 6%, which is 0.06 as a decimal. And our time, our number of years, is 10 years. So we're doing option A, which is the simple interest. The amount of money we're going to have for 10 years is going to be $1,000 times 1 plus 0.06 to the 10th power, which you would probably write as 1,000 times 1.06 to the 10th. So every year we're getting another 6%, right? It's 1,000 times 1.06 times 1.06 times 1.06 10 times. So that's going to be 1,000 times 1. I've got it literally written down right there. Why am I copying? Well, fine. It's too late. I've already done it. So we get approximately $1,790.84. But what I really kind of want you to think about with this one is that each year we're getting 6% more. So, right, $1,000 after 1 year, we're going to have $1,060, obviously. After another year, we're going to have $1,123, right? It's another 6%. After another year, we're going to have $1,191, it's another 6%. So every time you just keep multiplying by 1.06 to get to eventually having this after 10 years. Okay, here's the difference I want you to see. If we do it the second way, where we're compounding monthly, so here's what the formula is going to look like. And I should, sorry, I've got myself covered up here. So I don't need to see me, but I do need to see that to make sure the board is actually visible. So I should be a little more cleared up. So here, it's the principal times 1 plus, now it's going to be the interest rate divided by the number of times we're compounding to the 12 times 10 power. So what's happening here is this is going to be 1,000 times 0.06 divided by 12 is 0.005. And you can divide 0.06 by 12 very nicely. So 1 plus 0.005 is 1.005. To the 12 times 10 is 120th power. So here's the idea. Instead of calculating the 6% of interest at the end of the year and then doing that 10 times, what we're doing here is we're calculating a 12th of that. So 1/12 of 6% is 0.5%, right? I'll write this over here. 0.005 is 0.5%. And what we're doing is instead of calculating 6% a year 10 times, we're calculating 0.5% every month. And then we're doing that for 12 months in a year and then for 10 years, so 120 times. So the difference here is that in 1 year, we're not just going to end up with 6% interest, right? We're not just going to get $1,060 at the end. Instead, in 1 year, which would be this to the 12th power, right? Because we'd be doing 12 times 1, 1,000 times 1.05 to the 12th is going to be, that is clearly not right. It's clearly not right because it's at 1.05 and it's just at 1.005. Let's try that again. I got a number that was way too big. So here's the thing. After 1 year, let's put this up here. So 1 year compounding monthly, if I did 1,000 times 1.05 to, sorry, 1.005 to the 12th, you end up getting $1,061.68. So not a big difference, but it is a difference, right? And that's going to compound. Here, after 1 year, you'd have $1,060. Here, after 1 year, you have $1,061.68. So then if we do this calculation, throw this all into the calculator, we get that it's approximately equal to, what do I got here? $1,819.40. Again, not a huge difference, but there is a difference. And the difference is that here, after 1 year, you get 6% interest. Whereas here, after each month, you get 0.5%. So after 1 month, you get 0.5% of interest, which is going to be 1% is $10, 0.5% is $5. So after 1 month, you're going to get $5. And then in the next month, you're going to get another $5, but you're also going to earn interest on the previous $5. So you're getting the money, the interest you've earned more frequently, and it's getting compounded or earning interest once you've got it. Hopefully that is relatively clear about what's happening. So all other things being equal, the more frequently you compound your interest, the more money you're going to accrue, or the more value you're going to accrue. Yeah, all right. That's kind of the whole idea. There is kind of one very important idea that comes into play here with this. Yes, that is 12 times 10, exactly. So that, and again, I'm going to say this one more time because I think it's worth saying. Here, we compounded once a year for 10 years. So we have 1.06 to the 10th power. So right, 6% every year for 10 years. Here we did 6% compounded monthly. So we divided that 6% of interest up into 12 equal 0.5%, right? We're getting 0.5% after the first month, 0.5% after the second month, 0.5% after the third. If you take 0.5% and multiply it by 12, that's equal to 6%. So here we're getting 0.5% every month, but then we're doing it for 10 years. But 10 years is 120 months. So you take the number of times per year times the number of years and you multiply those together. Hopefully that makes that clear. So you're not getting as much interest every time, but you're getting the interest for more times, for more intervals. All right, let's look at some other questions. So yeah. So again, everything's just getting thrown into this formula. We usually know all the pieces except for one piece. So for example, suppose we invested, and so I'm going to read the question, I'm going to write down what makes sense, meaning the pertinent details. Suppose you invested $5,000 into a savings account. So our principal is $5,000. It pays 4% interest. So our interest rate is 0.04, right? That's 4%. Interest, and it's compounded weekly. So if it's compounded weekly, that means our N, the number of times we're compounding per year, is 52. Yes, I know, and everyone knows there aren't exactly 52 weeks in the year. If there's 52 weeks and 1 day or 2 days if it's a leap year, we don't worry about it. We just say it's 52. So the question here is, how long until the money doubles? So we're going to set everything up, right? Often I will write down the equation again. So I should be able to put a value in for everything in this equation except for the thing I'm trying to solve for. Since I'm asking how long until the money doubles, I'm really asking for what is the time value, the t value. So that means the A, the P, the R, and the N, I should be able to substitute in actual numbers for. So the principal is 5,000, which means the amount, if I'm trying to figure out how long it takes to double, that means my amount should be double that, so 10,000. So I should be setting 10,000 equal to 5,000 times 1 plus my interest rate, which is 0.04, divided by my number of times I'm compounding, which is 52, to the 52 times t power. Now, it's worth noting that 0.04 divided by 52 is not an exact number. If you take 0.04 divided by 52, it's a decimal that doesn't end, right? It's 0.000769231. You could round that, but what I think is a better thing to do if you're using a calculator is to just keep that number and then kind of do the calculations with it. So here's what I'm going to do. I'm going to do I'm going to write it down this way, but in my calculator, I'll show you. So I'm trying to solve for t. So I've got 10,000 divided by 5,000 equals 1 plus 0.04 divided by 52 to the 52t. That's a 2, right? 10,000 divided by 5,000 is 2. Now, if I'm trying to solve for this t, which is in the exponent, I'm going to have to take a logarithm of both sides. So I'm going to do the natural log of 2 equals the natural log of 1 plus 0.04 over 52 to the 52t. And the whole reason we take the natural log is so we can bring this exponent down in front. So the natural log of 2 is equal to 52 times t times the natural log of 1 plus 0.04 divided by 52. I'm going to divide both sides by 52. I'm going to divide both sides by the natural log of 1 plus 0.04 over 52. These cancel. These cancel. So t is equal to the natural log of 2 divided by 52 times the natural log of 1 plus 0.04 over 52. And then if I'm using a calculator, here's how I'm going to do this so that it comes out to be as close to the right value as possible. I'm going to deal with this part first. So I'm going to find 1 plus, so I did 0.04 divided by 52. So you guys can see that kind of. Yeah, you can see that. And I got that terrible number 0.000769231, right? Then I'm going to add 1. I get 1.0769231. So that's what's inside the natural logs. And I'm going to take the natural log of that. So I do that, natural log of my answer, and I get 0.0007689. And then I'm going to multiply that by 52. I feel like you guys are cool with me doing the rest, right? Multiply by 52. And then I'm going to do the natural log of 2 divided by that whole thing I just got. So it's going to be the natural log of 2 divided by my answer. Just like that. You guys can see that. I know there's like a terrible glare here, but you guys can kind of see that. And we get 17.33 approximately. And I'll answer your question, Alessandra, in just a second. So we get approximately 17.33. And I just want to point out that if you had instead abbreviated this and said this was approximately 1.00077, your answer at the end is slightly different. So approximating earlier on in the process can throw off your answer at the end by a little bit. Not a big deal in this class, can be a big deal, especially in chemistry. So it would take about 17.3 years. So a third of a year is what, 4 months? So about 17 years and 4 months to double our money. To answer Alessandra's question, why do we divide by 5,000? So if you're trying to solve for something in an exponent, you can't get rid of the base, right? So we've got some base to some power, but this coefficient we can definitely eliminate and get rid of by dividing both sides by it. So we divided by this so that we could just have this base 1 plus 0.04 divided by 52 raised to the 52t power so that we could solve for t. And that's always going to be part of the process. Whenever you're trying to solve for something that's in an exponent, you always want to divide out any coefficients here before you do anything else. Okay. So here's an important example that is not in the notes. I mean, it's in the notes that I've written, but it's not in like the official notes. But this is kind of, you might see this example when you take calculus again, or they might just kind of skip over it. It's usually more talked about pre-calc. This is a very, very kind of standard example to talk about a number that we've already talked about. But I'm not gonna give it completely. Oh yeah, go ahead, Nicole. You can either talk or you can type, either way.
Yeah, for the last question, for a quiz or for homework, would you want us to completely calculate it out to be 17.33? Or would we leave as...
Yeah, so I would say, in a normal classroom setting, if I was giving you a quiz in person and you didn't have a calculator, I would probably say you would just leave it like this. That's obviously not what we're in here. I would say, I guess I'd want to see, that's a good question. On homework, I kind of want to see both, which I know is like probably the least favorite answer you could expect. But on homework, I think I'd want to see, especially if they're asking for a number of years, like I would say, well, I want to see this so I can see that you know how to do this stuff. But then I also want to see the decimal approximation because that's what makes sense. On a quiz, I would probably just ask for the expression and not ask you to give me a decimal approximation. Yeah, that's a good question. I don't know if my answer is as good as it could be, but that is my honest answer. I'd want to see both on homework and probably just this on a quiz. I will try to be very specific. So, and I should also say, generally, when you're doing the homework questions, make sure you read what they're actually asking you for. But when I write the quiz, I'll definitely be very precise in my language so that you should know what you are being asked to give me. Yeah, good question. It's always good to clarify things like that. All right, so here is the kind of classic example of being a very cheap loan shark. So I'm going to loan you $1. So I'm a nice guy. You needed $1, I lent you $1. But I'm not that nice because I'm going to charge 100% interest. I know it's a cruel world, and I'm gonna loan you $1 for a whole year. 1 year, because I don't need the money back all that fast. So the question is, how much money will you owe me? And the answer is, it depends. It depends on how frequently we compound the interest. So if we do just simple interest, right? I lent you $1, it earned 100% interest, which is another $1. So at the end of the year, you're going to owe me $2. The $1 I lent you plus the $1 of interest. But if we compound it more frequently, you're going to end up owing me more than $2. So let's actually write it down. So here's our formula. The amount of money you owe me after 1 year is going to be the principal times 1 plus the interest rate divided by n, where n is the number of times we're compounding, to the n times t power. Now, in this case, everything is 1 practically, right? The amount, sorry, not the amount, the principal, the amount of money I'm lending you is $1. The interest rate, 100% as a decimal, is 1.00, which is just 1. And the time, the number of years, is also 1. So here's what our formula ends up looking like. It looks like the amount of money is 1 times 1 plus 1 over n to the nth power. I don't really need that 1 out there because 1 times anything is just whatever you've got. So here's what we've got. I'm going to make a little table here. I'm going to have in the first column the number of times we're compounding. And in the second column, the amount of money you're going to owe me, which is 1 plus 1 over the number of times to the number of times power. So let's take a look. So if you compound it 1 time per year or annually, you're going to owe me 1 plus 1 to the first power, which we already said is 2. Makes sense. $2. Okay, let's see what happens if we compound it semi-annually, twice per year. So I want you guys, before we actually do this calculation, here's the idea. If I compound it semi-annually, so here's the first 6 months. Here's the second 6 months. So at the beginning of the first 6 months, you just owe me the $1 back, right? But you're not paying it back because it's not the length of the loan. So then after 6 months, you're going to earn, well, it's been half the time, so you're going to earn half the interest. Half of 100% is 50%. 50% of $1 is 50 cents. So you're going to get, or you're going to owe me an additional half a dollar. But now the amount of money owed is $1.50, and that $1.50 is what's accrued. And now you have to earn. Now I'm going to earn interest on that. So after another 6 months, I'm going to get the other half of the interest, the other 50%, right? Because half of 100% is 50%. but 50% of $1.50 is 75 cents. So you're going to owe me, or I'm going to earn another 75 cents of interest, which means at the end of the day, I'm going to get $1 plus that I lent you, plus 50 cents of interest, plus 75 cents of interest, which is going to be $2.25, which is what you get if you use this formula. It's going to be 1 plus 1/2 squared. And I think fractions are much easier to deal with here. 1 plus 1/2 is 2 halves plus 1/2, which is 3 halves. And 3 halves squared is 3 squared over 2 squared. And 9 divided by 4 is 225. Right? It's 9 quarters, which is 8 quarters, which is $2 plus 1 quarter, which is 225. All right, so look, charging you semi-annually instead of annually, or I should say compounding semi-annually instead of annually, got me an extra quarter. Totally worth it. What if you compound it quarterly? Well, then it's going to be 1 plus 1/4 to the 4th power, which is about $2.44. So you might start asking yourself, well, is there any limit to this process? If I keep compounding it more and more frequently, can I get infinite dollars? I mean, that would be kind of cool. It's not true, but it would be kind of cool. What about, can I get $3? If I compound interest a lot per year, can I get $3 back? The dollar I lent you plus $2 worth of interest. Well, let's see. If we compound it monthly, it's going to be 1 plus 1/12 to the 12th, which I encourage all of you to check some of these with your own calculator if you want, just to see that I'm not a liar. But if you find 1 plus 1/12 to the 12th, it's going to be about $2.61. So compounding it monthly, I get an extra 61 cents versus just versus annually. Now let's continue on with our table here. If we compound it weekly, right, so n is 52, then the amount of money I'm going to get is 1 plus 1/52 to the 52nd power, which is approximately, what have I got here? $2.69. And it looks like we're running out of steam. I don't know if we're going to get to $2 to $3. If we do it daily, just 365 days in a year, 1 plus 1 over 365 to the 365th power is approximately $2.71. It's actually, I wrote this one out. It's about 2.71. 456. So there's a lot of this. 456. Sure, that looks like a perfectly fine place to end that. So here's the thing. We're not going to get to $3. Boo-hoo. What we are getting closer and closer to is that the more times you compound per year, so if you compound many, many, many times, right? If the number of times you're compounding gets larger and larger and larger and larger, the amount of interest you're getting closer and closer to getting, or the amount of money that you're getting closer and closer to is approximately, well, is not approximately, is E. Where E is the number that's equal to 2.714, sorry, 1, not 4, 8 to 8, etc. So that's kind of the big deal here, is that if you let the number of times you compound the interest in this particular formula get larger and larger and larger, more frequently, get infinitely large, then the amount you're getting closer and closer to actually is the number E. This is an important limit to be aware of. It definitely comes up in calculus. All right, so that is what we've got. And it comes up in the next formula, which is this right here. So if you compounded interest an infinite number of times per year, well, there's a better way of saying that. It's called compounding continuously. So continuously compounded interest here's the formula. The amount of money equals P times E to the RT power. Where again, the usual things. A is the amount after T years. P is the principal. E is the number E. R is the interest rate as a decimal. and t is the number of years. Right, it's the PERT formula that I imagine some of you have seen before. So, and again, the idea here is that n is extremely large. And it really does just come from taking this previous formula and letting n get very, very large. That's the whole idea. So we can use this formula too. Suppose we invest $100 at an interest rate. Oh, no, sorry, we don't know the interest rate. That's the question. So $100 in an account that continuously compounds interest. So here's the only thing. There's basically 3 different words that are going to tell you what the formula is. If the word is simple, and if they say we're compounding interest using, or if they're saying we're earning simple interest, your formula is going to be, sorry. Let's do this example first, and then I'll say the thing I'm trying to say. So $100 in an account that continuously compounds interest for how long have we got here? For 20 years. At the end, after those 20 years, we have $500. What was the rate? All right, it's a lot of words for throw it all into the formula. So here's our formula. A equals PE to the RT. We know that the principal was $100. We don't know the interest rate, right? That's the question. We know the time was 20 years, and we know it's supposed to equal the amount we have after 20 years, which is $500. So then we're just going to solve for R. I might have enough room, but let's go to the other side so that I actually have enough room. So I'm just going to write that equation down on the other side.
I have a quick question.
Go ahead.
How did you get E for that equation?
Sure. So that's the thing, is that so the E came from reading the words continuously compounds. So if we're being told that we're continuously compounding, this is the formula that we're using.
I understand. Thank you.
I'm going to speak more to that in just a second. Let's do this example, and then I'll say more words about that.
Okay.
So our formula was, I forgot already, 500 equals 100 e to the r times 20. And just like in that other problem where we were trying to solve for something in the exponent, before we can do that, we have to get rid of this coefficient here. So I'm going to say 500 divided by 100 equals e to the, I'm going to rewrite this as 20r. It's fairly common that when you have a variable times a number, you write the number first. So then this is 5 equals e to the 20r. And then I'm going to take the natural log of both sides. Natural log of 5 equals the natural log of e to the 20r. In this case, we can bring down the power, or we can just say that the natural log of e to the something is just something, right? Because this really says log base e, right? Log base e of e to the stuff. So you're asking e to what power equals e to this power? Well, it's got to be that power. Or I can show you the steps. Let me show you the steps. Natural log of 5 equals 20r times natural log of e. But natural log of e, that's just equal to 1. So then solving for r, natural log of 5 equals 20r, divide both sides by 20, and we get that r is equal to natural log of 5 divided by 20. And then I would actually use a calculator because, so again, if I'm asking for the interest rate, it's not super meaningful, right? If we actually calculate this via a calculator, we get approximately 0.08. So our interest rate is approximately 8%. So let me talk about the words that kind of tell you which formula you're supposed to use. So if we say that we are earning simple interest, that means we're going to use the formula A equals P times 1 plus R to the Tth power. If we are compounding interest, and so the thing about compounding is you have to know the number of times per year. So we're compounding interest n times per year. And this is really where you have to pay attention to, like, if they say quarterly, that means 4 times per year. If they say semi-annually, that means 2 times per year. If they say weekly, that means 52 times per year. But if they're compounding interest more than 1 time per year, then the formula is going to be A equals P times 1 plus R over N to the NT power. N times T is your power. And then the third language thing is if we're compounding interest continuously. Then that's when we have to use the formula P times E to the RT. Sorry, my R was terrible there. Where E is just a number, right? E is the number that's approximately 2.7, but there should be a button on your calculator that says E or E to a power. So these are the 3 different formulas. Simple interest, compounded n times per year, compounded continuously. Someone might also use the words you're compounding an infinite number of times per year, but no one should really be saying that. I don't think that language is used in our homework assignments at all. So hopefully that is clarifying. Okay, we got plenty of time. So that's what we got. Let's look at the next question. We got 2 more questions. Your goal is to have $2,000 in 4 years. So goal, $2,000 in 4 years. So I just want to point out already, before I even do anything else, I'm thinking, okay, this is probably the amount of money I want to have, and this is the number of years. And the rate of interest is 10%. So interest is 10%, and our interest is being compounded monthly. How much money do we need to start with? How much do we need to invest? Okay, well, again, here's what I know. I know the interest rate is 10%, so I know that this means that my R is equal to 0.10, or just 0.1 if you want to drop off at 0. I know that compounded monthly means that my N, number of times we're compounding per year, is 12. And how much do we need? That's asking the question, what is the principal? So we've identified all the parts. Now we just have to figure out what's what. So since we're compounding more than 1 time per year, we know we're using the formula A equals P times 1 plus R over N to the NT power. We're just going to throw all the things we know in and try and solve for the one thing we don't. So we're trying to solve for P. So we've got that, let's see, 2,000 equals P times 1 plus 0.10 divided by 12 to the NT, so 12 times 4 power. And this one's actually pretty easy to solve, meaning, well, I mean, right, if I'm just trying to isolate this, I can divide by all of this. So I can say that 2,000 divided by 1 plus 0.10 divided by 12 to the 4 times 12 is 48 to the 48th power. That's what my P is going to be. And then we break out our calculator and say, okay, this is going to be, so P is going to be approximately equal to 2,000 divided by 1 plus 0.10 over 12 is 1.008333, approximately. It's actually a 0.333 forever to the 48th power. So then I would jam it all in, right? I would do it as, I'm just going to say the things, I'm not going to show you every step. I would do 0.1 divided by 12 plus 1, sure, to the 48th power. And then 2,000 divided by that answer. And I would get approximately $1,342 and 86 cents. Which is a slightly different number than I have in the notes, because in the notes I actually used the decimal approximation 1.008333 instead of using 1 plus 0.10 divided by 12. So if you use a decimal approximation earlier on, it'll slightly change your final approximation. It's not a big deal. I'm not going to worry about it if your answers are a couple cents off from someone else's answers. Okay. One more example, and that'll be all for today. And then we can eat some lunch. I am hungry. So, quick story. Yeah, we got time. Over the weekend, my good friend, one of the other specialist husbands, actually, he cooked a whole pig, but he did a cochinita pibil, where he, cut it up, marinated it in the achiote and all that other stuff, put it in a box, buried it in the ground with like fire and rocks, and made a lot of very delicious pig. And there are lots of leftovers, and I'm going to eat that for lunch. So you should all be jealous because it's delicious. I wasn't really saying this to brag. I was just like, it was a very neat experience seeing him do it. It was amazing. And he is an excellent cook. Like, he can cook just about anything, really. But it was really kind of cool. Well, it was really hot, actually, but it was really cool just seeing the whole process. And this is the first time he's done this particular version of cooking a whole pig, but it turned out really great. And he's definitely going to do it again. So it was very exciting and very delicious. And I would share it with you guys if I could, because there was a lot of meat. I think before it all got cooked, I think after they trimmed off all the excess parts, there was still about 50 pounds of just meat. So obviously, if you're vegetarian, I wouldn't share it with you because you wouldn't want to eat it. But if you were not vegetarian, I would totally share it with you. All right. Sorry. Got a little sidetracked there. I'm too hungry. Last problem. So we have $1,000. So let me read things and write down the information. So you have $1,000. So our principal is $1,000. So the only problem with class right before lunch is I'm always thinking about what I'm going to eat for lunch. And I want to grow it to $2,000. So we want the amount to be $2,000. This is also an example of doubling your money, right? If we're starting with 1,000, 2,000, we could also say, I want to double my money, and we'll do the same thing. We want to double the money in 4 years. So that's going to be our time. What interest rate? So what does R need to be if we are compounding continuously? If interest compounds continuously. Oh, and there's actually kind of an interesting thing that's true here that I'll mention here. All right, so we're going to set the formula. Compounds continuously means we're in the A equals PERT, P to the RT situation. 2,000 equals 1,000 E to the R times 4. divide both sides by 1,000. So 2 equals e to the 4r. Take the natural log of both sides. So the natural log of 2 equals the natural log of e to the 4r. But the natural log of e to the 4r is just 4r. So the natural log of 2 equals 4r. Then divide both sides by 4, and you get the interest rate is equal to the natural log of 2 divided by 4. Natural log of, I feel like I've made a mistake somewhere. No, I don't think I have. So that's going to be the natural log of 2. Natural log of 2, which is about 0.69, I believe. Yep, divided by 4. It's going to be about 0.17. So that's going to be an interest rate of about 17%. And the reason I mentioned this is because there's this kind of, you may have heard, I don't know, you may not have heard. I remember when I was learning about interest rates the first time around, there's kind of like this thing called the rule of 70, where take 70 divided by your interest rate is the amount of time approximately it takes for something to double. And that's true here, right? 70 divided by your interest rate, 17%, is 4.11, and it's taking about 4 years for our money to double. The reason this is true is because the natural log of 2 is about 0.7 or 0.69. So if you're you're getting the 2, right? If you're doubling, you're getting 2,000, or sorry, you're not getting 2,000. You're getting your number that's double divided by this number. You're always getting 2 over there. And then when you take the natural log of both sides, you're always getting the natural log of 2, which is about 0.7. And then 0.7 divided by your interest rate is going to be the amount of time it takes to double. That's why there's this rule of 70. It's kind of neat. It's not exact, it's approximate.